Because of the time I have taken.
वैक्यूम में तो 15 मिनट लगते हैं, 10-15 मिनट.
So now what is the sample holder that you are saying? This is the stage view. ठीक है?
Okay, sir.
nine sample 9 sample carousel.
ओके
ठीक है?
सर.
अभी ये है तो so if you go to the stage navigation system from here settings, you go to sample holder. Sorry. So you can choose any holder that you are going to use. Understood? So that is the only setting that you need to change here, and then you can use any of the sample, you know, where you know at exactly the location where you are insert. Yeah, sample, put your sample and do start imaging. Insert the stem detector and start imaging.
ओके सर.
But the main challenge here is the sample preparation has to be accurate because it is not a 200 kV source, it's a 30 kV source. So the number of transmitted electrons are quite limited depending on your sample thickness. If you are working on metallurgy, depending on metallurgy would be very difficult, I will say. Powder sample, biological samples possible.
ओके.
So some signal has to be transferred. Sample preparation has to be more accurate. I mean, you have to be more careful. Yeah. So vacuum is used. So we can. So now with small demonstration of how things can be done. So in the second half, you can have your hands on.
ओके सर.
Yeah.
Sample on limits.
Yeah. Yeah. So this is called known as joystick basically, where we can control the stage. So stage has the 5 sort of movement, 5 movements:
ओके सर.
X, Y, Z, R and T, rotation and tilt. So this is known as a joystick and this is unique, huh? Unique for this. Generally these joysticks are not available. The control panels are available for other manufacturers to control the stages actually.
Or different characterization, the working distance will be different.
Yes.
This is the donor.
This is the 7.
Number 7.
Number 7.
This one.
Yeah. Yeah.
Alright.
So in the position number 9, I have inserted this. you're generally आप generally इस क्रॉसर पे काम करते हैं क्या? So basically, what is our purpose here? Now we have set this EST is already set actually when we started the experiment at 5 kV. So depending on your sample, you can increase and decrease, and what kind of signals that you are getting from your sample, depending on that you can change your kV here. And also if you are changing the detector, so here. So here, see the detector. These are the detectors available when this signal A. Everybody can see, right? Here the signal A. Here we can choose the detector as per your choice. So we have the secondary electron detector chamber AC. We have this in-lens AC which is mounted in the column. One detector is the VP AC, that is AC detector in VP mode. Secondary electron detector in VP mode, that means low vacuum or the variable pressure mode. Third one is the BSD detector for compositional contrast.
Okay.
And last one is the stem detector
Okay.
from there. So these are the detectors available in your system basically. So I mean at different places you find different combinations of the detector. So basically now I am trying my first job is to trying to focus the sample. Now genetically focused. Again I am increasing the magnification.
Here we change the magnification like a TM or a different.
Just coming
Yeah, this one.
About the process.
Yeah, so the magnification is a factor here basically. It's a factor. I mean, I think it will be probably for every microscope. It is basically electron microscope. It is basically the same. Magnification is nothing but the factor. So it is. Sorry, I'll go to his question because it is bit important.
Yeah, sure, sir.
So magnification is the factor. What is the factor? So the screen, this particular screen size that we are observing, and divided by the area that we are scanning with the electron. So this is the magnification factor. This is nothing but the magnification factor. I mean I do not have any very clear idea of the term, but electron microscope means the same. I think it would be same only because it is the electron microscope. I hope I am correct, sir. Yes.
Yeah, I mean, like,
Right.
these are the fundamental, like your
Yeah.
optical microscope
Correct.
and TM are projection microscope. So you project an image, right? But this is a scanning electron microscope. So as sir rightly told, your magnification is nothing but the area of the screen divided by the area you are scanning,
Okay.
right? So because you are collecting data here pixel by pixel, right? Like point by point, you are rastering at such a fast position. One really needs to think, like, if I were to ask you, like, what limits the resolution? We talked about it today, like, what limits, because you are all physics students, right? You heard about the Rayleigh criteria?
Yes, sir.
Rayleigh criteria, does anyone remember? Airy stress, airy rings. If a light wave passes through an aperture, what do I get? Or Young's double slit experiment, everyone knows. Interference, contrast and all, right? But before that, if a light wave passes through an aperture, what will you get? Huh? I get a central spot and then I get concentric rings. Remember that, right? Concentric rings and also that, which function is this in maths? It is sin x by x whole square. What is known as the sinc function. So try to plot it, sin x by x to the power whole square. You plot it, that will give you the intensity. So can anyone tell me, sin x, everyone knows it goes from +1 to -1, How will sin square x look like? Sin square x, how will it look like? Will there be anything negative?
No, sir. Only
because it is
positive.
square, so it will just go from 0 to 1, 0 to 1, 0 to 1, right? So you will get only these values,
Positive
right?
side.
You won't get anything negative, right?
Yes.
So the sine square x by x square function is like the intensity profile what you get. Now if you have this peak, how close you can bring two peaks? Did anyone has any idea? So I say that minimum, the first minimum of my one peak matches with the maximum of the first peak, right? That gives you the Rayleigh criteria. So your resolution in optical, if I ask you what is the resolution, can you comment? Like resolution of human eye? Or how much can we resolve? Can we see with our eyes?
Banana.
Ballpark, millimeter, kilometer, centimeter,
Mm.
mm से भी नीचे होता है. Yeah, about 100 micron, right? उसके ऊपर अगर जाना है तो then you go to an optical microscope. But then you can't go beyond optical microscope also because you will get empty magnification. So optical regime, optical wavelength, does anyone know? Visible light wavelength? 400 to 700. So as a ballpark, you can say it is lambda by 2. It is 0.61 lambda by the numerical aperture. Is the rule is like the Rayleigh criteria. So you can say roughly lambda by 2. So it is 200 nanometer. So if you need anything lower, then that is where you go to a SCM. But this is a scanning microscope. It's a scanning microscope. This is much similar to an AFM. And a TM is similar, not to a SCM. TM is similar to an optical microscope. So that fundamental difference is there. So what Sir told is very correct, that you just simply choose the area that you are scanning on the sample and projecting it on the. So its interpretation is also different, right? But you tell me, don't you get a feel when you look at the sample as if you are looking from the top? Just like you are seeing in an optical microscope, right? So what is the optic axis of a SCM? Optic axis you understand, na? When you look at it in an optical microscope, you are sitting on the chair. You are seeing through the eyepiece. But still you feel as if you are seeing from the top, right? Why? You guys should do a course on microscopy, huh? NPTEL, you know NPTEL?
Yes.
So NPTEL, there are many nice courses on microscopy. You can please do that.
Okay.
You put a mirror, na?
Yes.
So though you are sitting in your eyes, you feel you are in the straight line. So you are along the optic axis. So here what detector they put, the detector you give, I think in SE2 you give positive bias, right?
Yes.
Positive bias.
Yes,
So because of the positive bias, it sucks all the secondary electrons. So it does the same thing that a mirror will do. Right? What the mirror does, in an optical microscope, whatever light is getting reflected from your sample, the mirror reflects it back to the eyepiece. So though you are sitting here, the sample is over here, you are in the same optic axis, right? You are in the optic axis, so therefore you feel as if you are looking from the top. The same thing over here, what you are seeing is from the detector over here, which is not along the axis of the sample. It is sitting over here at some angle. But because it has a positive bias, it sucks in all the secondary electrons. So you get a feel as if you are looking from the top, right? Because they show nice spherical particles, you will see as if you are looking from the top. While your detector is not at the top. Is this the SE2 detector? Or somewhere should be here. This looks like this is the optical light.
Yeah.
This is the,
yes.
So see, SE2 detector is here. It is not in the column, but still you get a feel as if you are seeing from the top. So guys, please do see. You won't be able to learn in a day or two. Please read textbook. Which textbook will you see if you want to study about SEM or materials characterization? You know about Brandon and Kaplan?
No,
The book by Brandon and Kaplan.
No.
At least go through that. If
Okay.
not, if you want to become master in SEM, read this book by who's there? Goldstein. Now you don't even have to steal. All these books are available on internet. So you can read on your smartphone. Okay, please do that.
I think it is better that we complete another because we have to go through another demonstration. After lunch, then we can start the hands-on training, because second half we keep it for the hands-on training. Maybe a batch of 5 or batch of 10 maybe come together, they sit together and they start exploring how the things can be controlled. It is a very short time to learn the to operate, but operation is not a very difficult thing, as sir. You can sit for 1 or 2 days, operation you can learn, but at least what are the effects of the parameter, that you need to understand, so that next time you can come, you can tell that you can change these parameters so that your image would be perfect. That is important. So maybe we can start because there are another 20 guys who are waiting. We have to finish it. Yeah.
Okay.
The donut on the right hand side.
Hey, this one?
Yeah. We capture one single donut there. Perfect donut. No donut.
Donut.
It's a fact.
स्फेरिकल भी है एकदम सर्कुलर भी है.
I'm so happy I can see one single donut.
At least your sample is not damaged. I guess.
Yeah.
It's all right.
Maybe show them a bit the wobble and the
Yeah.
Just
So,
a quick glance.
so quickly, these are the controls of the stigmator coils. This is nothing but the coils that are present in the column to control the
Electron beam.
error arises due to the imperfection of the coils. So these are all electromagnetic coils, right? I mean the condenser objective coils, and these are manufactured by the human being, and so that is why the coils are not perfect coils. There are some errors or aberrations present in the coils, and due to that particular issues, the electron column has some error. I will say electron beam has some error which is known as stigmatism error. To control that, we have these stigmator coils present in the system. So okay, just quickly maybe I will go to some other region, I guess, right? This one only? Okay.
take one see my first page.
Okay. Okay, here I will show how the stigmatism can be controlled. Here we have this one. It's almost correct and it's still. So now we are focusing that particular region only. Okay. So we put the reduced button. So it means we are scanning for this particular region only. Now I'm changing the. So first, before you start the stigmat, you are not touching the stigmatizing coils. Just make sure that your focus, maximum focus you have done. The focusing is more or less correct. Since it is actually the perfect image you actually, this is more or less perfect, so you may not be able to understand where exactly if you change the focus, but when you are actually practical sample, maybe the focusing won't be that great. Okay, you change the
Just to show you.
okay, so now I am doing the stigmatism correction. So you see the I have actually destroyed the stigmatism correction. So you see this whatever the spherical, that goes into the elliptical mode basically. You can see this. Now I'm changing it again to corrected. Now again this one. I'm doing this one. You see in the another direction you will see the ellipse. Basically in another direction, right? Earlier it was there. Now elongated in the other direction basically. So this is how the stigmatism. And another thing I will show you is the oblong.
So we need to destroy your focus.
No, no, it's okay. It's okay. I think. So you are now understand what may be the significance if you don't do the stigmatism correction, right? Your image will be absolutely different, right?
Will be distorted.
Distorted. Yeah. No, okay. Let me show the opening. So it's oblique, right? It's oblique. Oblique.
Wobbling is very important when the magnification is very big. When you go to 50 to 100,000, wobbling very important. If you take 1,000, 2,000, don't bother.
Bother.
Don't waste your time. My donut not fully circle. Not a perfect circle.
Sorry.
The donut not fully circle.
Okay.
Almost perfect. Just come first. Slightly. Yeah.
Its oval is also perfect, right? We have to destroy the oval. Oval is also perfect.
You can destroy and show, then you do that. This picture is too perfect.
Yeah, too perfect. So okay, now I will show the openings. Yeah, now we can see. So you can see this particular feature, right? There is a feature that you can see on the middle part of this reduced button. So that particular feature comes at the same place. You focus and defocus, it comes at the same place, which means your electron beam is exactly at the perpendicular. If now I try to destroy the my settings. Okay. How to destroy it? how will I do this? This
When
happens.
you make the oval, just
Okay.
Just,
Now you see it's been moving. Right. So when suppose you are doing your sample analysis and at a very high magnification you are not very clear picture, you do the orbling, you will see this kind of thing, that your sample when it is focus and defocus, it will the same feature will not come at exactly the same place, because your sample is not in perpendicular. So you control this particular thing. Now I am destroying the oval. You see it's like moving. It's moving actually.
Second batch.
Yeah.
सेकंड बैच अभी तो नहीं होगा, लंच करवा के फिर करना।
Okay, ठीक है.
we'll lunch first, then second batch.
Okay.
हाँ,
Okay.
But maybe in 1 or 2 minutes we wrap up. We take them for lunch.
Yeah.
We show the oval, then we go.
So now I'm trying to fix the oval. Here one thing is that
So you don't want like this.
huh?
You don't want like this, you don't want like this.
Yeah.
You want to be like this. Because when they focus, defocus, you want it to be on the same plane. So you want it to look like this. You don't want like this. You don't want like this. Right? Now you see it's left and right.
Yes.
So meaning the X got problem. Right? How do we need to fix the logo? So basically, if you turn to one direction, it becomes worse. Turn the other direction.
Okay.
Not the same.
स्टोरेज भी खत्म हो गया।